Uh, Welcome to lecture number 4. So this time we are starting with the main and core lecture of the advanced data management. So this topic is about distributed data management. So here we will going to discuss the important concepts about distributed data management systems. Okay, so far we were discussing centralized database management system. Now the database or data management systems are now distributing across multiple computers or multiple nodes. So from this lessons, we will examine the data management in distributed systems. So a distributed system is composed of multiple computing node and data. I mean, it's here we are not only sharing the data, but as well as softwares can be partitioned or sharded, okay, among multiple nodes. So partitioning or sharding, I mean, these are the same thing. So this is one of the concept we will be discussing. But in simple terms, we are putting the same data on multiple nodes. Okay, this is called partitioning or sharding. So data can be replicated in multiple nodes. Now, before going in more details, uh, let's discuss the some of the basics of the basic of distributed systems. But before starting of the basics of the distributed systems, discuss some of the advantages of distributed systems. So they can avoid a single point of failures, like if you see in our previous MySQL databases, if the database fails, so I mean that was a single point of failure, so the overall database is gone. So it is, I mean, if single node stop working, like in a single point of failure, so I mean the whole system is non-operational. Okay, it may all allow to hold larger amount of data. I mean, this is the benefit as compared to the benefit of the, I mean, the traditional databases of the distributed data management system that they can hold a huge data and it can improve the efficiency. I mean, that's a very important aspect. And it is also very cost effective. I mean, we are scaling out here. So we are dividing the load in computation across multiple computers. So we are not scaling up, we are scaling out actually here. Uh, so in terms of hardware, it's also really effective. So at the same time, they introduce also more complexities as well, and because the more machines are involved, and it's also now on a network. So this is the complexities associated with the distributed data management systems. Okay, now the basic of distributed data management systems. So we are sharing the memory, we are sharing the disk, we are sharing nothing. So if you see that sharing a memory, so nodes share main memory like RAM, communicate via shared main memory. So they are also sharing the disk. Nodes have a local memory, but shared disk communicates via shared disk. And there is also possibility of they are sharing nothing, like nodes share neither memory nor disk. So they're only connected through a network. So communications by message exchange only. Okay, so how the tasks are distributed in the distributed data management systems. In the database, in data management systems, okay, the task distribution or the workload distributions is based on a three way. The first one is client server. So, I mean, one of them is acting as a server node and responsible per task, and other nodes are clients requesting sending them to them. And the second one is peer to peer. I mean, this is also really famous. Responsibilities are shared across all nodes or among all nodes, or multi-tier. So in the multi-tier node share responsibility for the task, they are structured in a hierarchy. So in a hierarchy way, that nodes in a given level tiers are responsible for particular subtasks. The most commons among the multi-tier is a three-tier. So I mean the first hierarchy, I mean the hierarchy of the presentation layer is the clients, In the application layer is a computation, in data layer is access, and they are managing the storage. So that's one of the famous among the multi-tier. So how this is they are distributing the loads and the data among the or tasks in multiple nodes. Okay, so before going to the Coff theorem or in Pascal theorems, it is important to understand about the uh, three different concepts about the consistency and availability and partitioning tolerance. Let's even cover it here directly. Okay, Cobb theorem directly discuss that. Okay, it's important to understand the concept. It's really good. Then we will start the Cobb theorem. Okay, we have a three property: consistency, availability, and partitioning. So partitioning tolerance. So far, we already discussed consistency in the transactions. So there are certain uniqueness and constraints are applied in formal methods. So the transaction should be consistent. So it's almost the same. But here in distributed systems, they means the data should be up to date, okay? In most recent right with no error. This is the consistent mean here. In availability, even every request to a working node receives a response, no timeout. So availability means that there should be no latency, and as the user's request or order the node request, the response should be available. And the third one is partitioning. So consistency is represented with C, availability is represented with A, and partitioning is represented with P. So system continues to work despite network failure or delays. That's really important. So they should have to tolerate the partitioning, okay? But what Cobb theorem says, and what is the idea of the Cobb theorem? So Cobb theorem says there is no distributed data management system can satisfy the consistency, availability, and partitioning tolerance. I mean, there is no certain type of system which can tolerate all of these three or manage all of these three different uh, constraints like consistency, availability, and partition tolerance. So this theorem says that for any two properties, DMS satisfies those two, but not the third one. I mean, among these two, they can to maintain two of them, but not all of them. So it can be designed since network partitions are unavoidable. We are taking the rest of the two based on the partitioning tolerance. So, I mean, networks are unreliable, okay? So network partitionings are unavoidable in practice. So in the real choice, we are choosing between the consistency and the availability. So the Cobb theorem are also called Brewer-Galbraith link. So we are choosing when the partitions are occur between the availability and the consistency. Uh, it is good to discuss here about the base a little bit here. So basically available soft state, eventually consistent in comparison to ESAID with the Cobb theorem. So what Cobb theorem is basically says, the Cobb theorem is prioritizing consistency, but in the compliant architecture of ACID, but BAC is basically most prioritizing availability. So if you see the partitioning, so when their partitionings are happening, so they are preferring the consistency, availability may suffer here. But if you see in the base, in which is prioritizing availability mostly in the MongoDB or NoSQL, and ACID compliance, which is prioritize the consistency, is mostly in the RDBMS, Relational Database Management System, or SQL. So in that case, the availability suffer, but in the partitioning case of the base, which prioritize the availability, there may be in data may be stale. Stale means um, out of date. Okay, the data is not refresh. In here, this thing will be suffering here. As we discuss here, the consistency means the data should be up to date. Okay, or you can also say the consistency will be suffering here. So we have seen an example that Postgre, MySQL, Oracle are using ACID and preferring the consistency, and BAC is referring availability, which is used by Cassandra, CouchDB, React. Okay, it's important to discuss here also what is basically available. It means strives to respond. I mean, the main idea is the availability, so prioritizing to respond. So the strives to respond in soft state means data might not be current. Okay, so they depend upon here. Okay, as we discuss here that they are suffering with the consistency. I mean, the data is not available here as the name B stands for the basically available. BA basically available. B means basically I mean available. S means soft state. So soft state is a one word acronym of this whole BAC. So soft state means the data cannot be here the most up to date. The reason why because this is a compliant of the BACE is prioritizing the availability. Okay, and that's why here is the consistency suffering. So may not be current. It's not necessarily may be current, but as they are prioritizing, so there is more chances that will not be the current. So eventually consistent. Eventually consistent means well coverage to consistency when no failure occurs. So they will be consistent where there is no failures occur. Okay, so they are prioritizing to be available, and the data is not here up to date because they are suffering. Okay, so the Cup theorem is an extension for the Pascal theorem. A Pascal theorem is basically developed on the base of the Cup theorem. So the Pascal theorem says, which is the body theorem. Okay, the Cup theorem was presented by Brewer Galbraith Lenk, and this is presented by Abadi. Okay, so here they are mentioning further steps. So they say when partitions occurs, choose between the consistency and availability. Okay, we discuss here thing, but there is a case else no partitioning is happening case. So what will be happening? So choose between the inconsistency and latency. Consistency remain the same and latency is now coming another important aspect here. So let's develop based on this more. So based on these two theorems, we are developing four different trade-offs. Okay, so if you see this trade-off, uh, in this trade-off, we have type, then we have a partitioning between consistency or ability. If there is a partitioning, so we see there is a consistency or availability. In the else condition, we see there is a consistency or a latency. I mean, there is no partitioning is happening. And what would be the examples? In the type simple means P means partitioning, C means consistent. In the else condition, we are again consistent. So these are the symptoms coming from the consistency, availability, and else partitioning, latency, and all these things. Okay. So we are discussing the first one. Okay, if there is a partitioning, so definitely we are prioritizing the consistency. In the else case, we are again prioritizing the consistency case. Okay, so we are making a four different trade-offs. So what would be the example of this one? This is definitely RDBMS or ACID systems. Those systems which are the compliance of ACID systems, so automatically they are applying. If there is a partitioning or no partitioning, so they should become consistent. Okay, if there is a partitioning and we are prioritizing the availability, but in the else condition, we are prioritizing the consistency. Okay, so these systems basically are base compliance systems or MongoDB systems. Okay, so partitioning has been occurred, but they are prioritizing here the availability, which we discussed last in the cup theorem. But here in the else condition, if there is no partitioning, but they are still consistency are preferring. I mean, the data is also available and it is also almost up to date. So else condition is actually introduced by the Pascal theorem. So they says that there is no partitioning, so we should divide between the consistency and latency. So this is the example of the base in MongoDB. We have the third case, if there is a partitioning and we are opting for the availability, in the else condition, we are choosing low latency. So the example of this database is Cassandra, React, and all these, okay? And if there is a consistency again, and in the else condition, let's suppose we have a low latency, we are opting and there is no partitioning. So the example Yahoo Peanuts, which is quite rare. The above threes are mostly usable, but the last one is quite rare. Okay, So here we have a note. In the note, there are several data DBMS allows configurability, like PostgreSQL Cosmos DB allows all four settings. So based on the configurability, we can choose between these configurations of the Pascal and the COP theorems. One of the important concepts we are introducing, that is the replication. Okay, and it is really important in the core concept in the DBMS. Okay, so what does replication mean? There is a minor difference between their application and sharding, so understanding this is really important conceptually. Replication keep copies of the same data on multiple nodes. The same is doing by the sharding, but there will be a minor difference. What they are prioritizing and what they over there the sharding prioritizing. So they are reducing latency. So here we are prioritizing the latency and improve reliability or availability. So in the replication case, we are mostly focusing on to improve the reduce the latency and improve the efficiency and reliability. Okay, or we can say reliability or availability. Better read scalability. We are also working here on a scalability, but only on read scalability. Okay, it means read heavy scalability. So there is again a challenge also associated with this. All copies must be updated. Okay, so for addressing of all copies must be updating, so we are introducing uh, three different concepts, which is really important to address these issues. Okay. Okay. As we said that with the replication, we are facing the issue of the all the data must be updated. Okay, and they should have to keep it update. So I mean. For there are three main families of methods we are introducing here. It is a single leader, multi-leader, and the leaderless replication methods. So to address that, how to keep the data most up to date. In the single leader, or we also call them master slave or active passive. So one leader accepts all rights, followers receive the changes via application log. So change stream also usually called. So the example of this one is like PostgreSQL, MongoDB, Kafka, and RabbitMQ. Kafka and RabbitMQs are the brokers of messages. So replication mode is synchronous. So leader waits all followers to confirm first of all, and consistency is very high, but latency is also high at the same time. In synchronous communication, I mean, they are sending in the real time, and they are waiting for the followers to confirm. But in the asynchronous communication, there is no need. Okay, nobody sends a log then acknowledgement. Okay, so consistency here is eventual, but latency is very weak. Okay, here I mean the response could be very weak here in the asynchronous. But when it comes to the hybrid system, so in the hybrid system, it is basically the follower sync and rest are asynchronous. So this is the both of them are latency and the consistency are medal here. One important aspect with a single leader we need to address that is a master slave or active passive. We need to address that is the handling of failures. Okay. See there, so there could be two types of failures. So one of them is a follower failure. It can be managed with the method of catch-up recovery. Follower has a log of a changes received. Ask a leader for all changes since last known point resumes. So, I mean, the followers are also keeping the log of the last updates. Okay, so when they catch up the recovery, so basically they have the log and to see their log, and according to log, they are releasing the new updates. Leader failure. So failure, I mean, this is the method through which we are recovering the failure. So we're basically detecting the failure using a timeout. Okay. So elect a new leader causes problems. So must up most up to data. So reconfigure followers. It means we are basically see that if the leader has been after a certain time do not respond, and we assume that leader has been failed, so we are electing a new leader. But electing a new leader is there is a consensus problem. For this consensus problem, we will be discussing the consensus algorithm next. It is most up-to-date data. I mean, we will be choosing those one which is having a most up-to-date data and reconfiguring the followers. So with the new leaders, we will reconfiguring the followers. But with the failure of the leader failure in the asynchronous communication replications, new leaders may miss recent writes, non-replicated writes are discarded. It's a violations of their durability, okay? And durability, we discussed that the lock once the data record is committed, it should be persistent, okay? But here the new leaders may be missing some copies of the data. In another case, it here happens here is split brain. Split brains means two nodes of things that they both are the leaders. So I mean here is the risk of the data corruptions. In timeout, too short equals to false positive during the network load spikes. So these are the three different risks associated with the failure risk of the leader, and it should be addressed. Okay, so associated problems of the above ones which we discussed here. Okay, between these two, follower failure is not that much complex, but the leader failure is quite complex. Okay, and it can burn many problem as we discussed in the failure or risks. Now we are going further. Replication lag. What is replication lag and read scaling with asynchronous communication? So we have I mean, this may cause that the replication lags the follower serving the reader only query. Okay, in this case, I mean, the lag is causing that I mean, the followers are serving the read only query can have outdated data. The system is not consistent here, so, but it's eventually consistent since such a replication lag can lead to strain issues. Okay, replication lag and read scaling with asynchronous. Okay, so when we are reading the scaling with asynchronous, so this replication lag problem can give a rise or birth to multiple strange issues, like we are discussing the read after write. What is this? So users write, then reads, so hits an outdated followers. I mean, when we are reading here, okay, I mean, read after write is inconsistency. One user writes some piece of data initially and immediately ask to read it. I mean, they have written and after they are asking for the writing, okay? Users write some piece of data and immediately asks to read, but that write is not yet available on the follower serving the request. So this is the problem, the description of this problem. So what is the solution? The solution is that routers users own reads, okay, to leaders or user timestamps to check recency. Based on the timestamps and request to leader, we can read, okay. And the second one problem, non-monotonic read. It is another problems when we are reading read scaling with asynchronous, which is an application like problem. And the second strange issue they are giving birth or rise to called non-monotonic read. Non-monotonic read is same user reads same data twice. So since never then older version. So I mean when they are see the same data twice, so the next time they are sees, I mean they are older version. So it means that a user reads the same data twice from first from a following having newer data, then from a following having the older data. So like mean if a users request the data or the one node the data is old and the other it's new. Okay, so this is the idea non-monotonic read. Initially they are reading twice, but one time they are newer and the other time is the older version. So assign each user to be consistent, okay, replica by user ID. So this is the solution to this problem we can solve to assign each users to a consistent replica. So based on the user ID, they will be reflecting to the users the most up-to-date replica. This is the solution for this problem of the replication lag problem. Inconsistent prefix read. What this problem is basically discussing, this is that event sends out a casual order like B before A, but at the same time when A calls B. So the idea is this is another called problem called inconsistent prefix. Inconsistent prefix is a user knows that a certain piece of data A must have been written before the another piece of data B, but reads them in a reverse order. Thus, this is the violation of causality. I mean, causality numbering or sequence. What is the solution for this? So ensure writes in a causal order are replicated in the same order. As it's written in the causal order should be replicated in the same order. This is the solution for this one. Now going to second type of family of resolving the most up-to-date data by the multi-leader application. And multi-leaders can accept writes useful across multiple data centers on multiple sites. Okay, one leader per site you can assign. Advantages, they are providing higher write performance. Okay, and tolerance for data centers outage. Okay, let's suppose if there is electricity outage or one data center has been gone or died, so the other will be provided in serving because we have multiple leaders having with different new or updated replica. So the main problem is here conflict resolutions when two leaders write to the same data. I mean, this is the main and the biggest problem associated with this one. Okay, I mean, when two leaders write to the same data, I mean, there's certain data that both two leaders are writing. I mean, the issue between the leaders, how we gonna solve that one? This is the important concepts we are dealing here. Okay, so there are two main strategies we are using between the problem solving of the conflicts during the multiple layers. The first one is called conflicts avoidance. So conflict avoidance is really simple. We are giving them the certain data ownership to certain leaders, so which they can accept and write to it on it. The second one is a convergent conflict resolution. So assign timestamps to write resolve conflicts later. This is actually not solving the problem, but they can reflect the problem, but later can be solved. I mean, like they are assigning a timestamps to writes, okay, and resolve conflicts later. But last writes wins or users prompt. So this is the again later on strategies they are applying. Okay, to multiple leaders, we are also having the leaders topology they are creating, like as we have a single user per data center or per site across multiple geographical locations. So we have a circular or star topology. Messages must be passed through multiple hops. It is less resilient and no causality violations. Here, it is less resilient, but the causality orders are kept in a sequence, and there is no violation of a causality. But we have another type of topology, it's called all-to-all. So it is direct broadcast. It is more resilient, but can cause a causality violation if a network's links operates at different speeds. That's important. I mean, if they are sending broadcasting the message of the topology of all leaders, but with a different network speed, so it can cause the causality order. So that was all about the multi-leaders application. So now we're discussing the leaderless replication, which is another important application method. Okay, in the leaderless application, no designated leaders or users are available here, but here we don't have a certain type of leader like in the single leader, and we don't have multiple leaders, but we here call them a coordinators. So users and coordinators both are sent rights directly to the multiple replicas. So there are multiple replica, and all these replication methods are totally depend upon the problem and the applications we are developing. Okay. So in this case, if we say that we don't have any leader and the users and coordinators both are rights directly to multiple replicas. Okay, and here we have two approaches. Like in leader's application, there, as we know, there is no leader or responsible for managing all these rights. So we have two approaches. The first one is called read repair. When reads detect an outdated replica, okay, let's suppose if there is a request for the read and they detect an outdated replica, it updates it. It updates it. So the another one is called anti-entropy. Okay, so they are looking in the background processes in computer replicas and fix the differences. So these are the two methods how they are definitely working entirely from the single leader or multiple leaders replication scheme. But here in this leaderless replications, we have a quorum of replicas in replicas. Okay, I mean, there should be certain quorums through which we need to address or how to guarantee that the read and write has been occurred. Okay, so write quorums W write must be acknowledged by at least W replica, and read quorums R reads must be sent at least to R replicas. So how we should know that they are guaranteed? So in it's really committed. So the guarantee is as long as I mean write replica plus the read replica should be greater than the in. I mean the current one. We are guaranteed to see the latest writes here in this case, and typically in is odd. So in is odd. So write is equals to read, and read equals to in plus one divided by two. It's a majority case, and slope quorum is nothing but the write replica plus read replica less than or equals to the higher availability, but it is low latency. But reads may be stale as they are prioritizing here higher availability like base, but latency will be affected here, and data could be chances like it could be outdated and not the most up-to-date data. And the default quorum settings where the write and read defines a majority, as we discussed above. Okay, like the n is odd in W, which is write equals to write replica equals to the read replica, which is nothing. In plus one divided by two is a majority. So the tolerant to node failure up to in by two can be failed in the system would still work. Okay, and there is a chances. So in some cases, one may require even stronger availability guarantee. I mean, there's a chances like in up to in divided by two can be failed, but the system would still work. This may obtain sitting by, as we discussed, that the slope quorum, write replica plus read replica less than or equals to n, and this strategy has the side effects of also reducing the latency. We discuss here it's a higher availability but lower latency. Okay. However, there is some probability that we will read out of the data, and this is chances even though it's prioritizing the higher availability. Okay, important concepts we need to understand here, like we have seen in three different applications, the conflict resolution. So we discussed with the version vector, or how version vectors are helping to address the conflict resolution. So version vector is each data items assigns a version number v and incremented one each writing. So when we are writing, so they are incremented by one. Each subsequent write must provide its own version number of W. If W is less than the current version, V, the write concurrents, both versions are kept. In here, it's not auto resolved. Okay, they are keeping both of them. The current version is less than from the write, so the detecting from here that this write is a concurrent. On the read, returns all conflicting versions. I mean, they are also in the read showing the current version and the conflicting versions, both of them. So clients will see between both of them. So which one is the most up to date? So another solution is multiple replica, maintaining a version vector. So one version numbers per replica per data item. So we are keeping one version number, but per replica per data item. this is exactly the part of the version vectors, the multiple replica idea. And we have another solutions of resolving the conflict resolution. It's called last right wins. Uh, Last right wins we also discussed, if I'm not wrong, in the above somewhere. Okay, so last wins rights, I think so we discussed in the quorums. Guaranteed to see the rights. Yeah, we discussed somewhere. I forget about it. Where? Let's give it continue. So last right wins means like in the conflict resolution, this is one of the main method through which we are handling the conflicts between the multiple layers, single layers, or leaderless. So keep the writes with the largest timestamp. The idea is with the largest timestamps mean that is the most recent one. Simple but risk data loss. Yeah, with this one we have the loss of the chances. Okay, with the last write wins. So we are losing one replica in the middle. Another one, which is called CRDTs, so conflict-free replicated data types, can auto resolve some conflicts. It is using by most modern database management systems. I mean, if you see the version vector system is not resolving actually the problem, but they are reflecting to the users, and the user will see upon that which one is the most updating. If you see the one reads written all conflicting version, client must resolve the issue. So that was all about the application. It's how to keep the data updating. Now we are starting the another important concept. It's called sharding. As we said, sharding is mean partitioning. So it's more relevant like replication, but this is a little bit different and they are prioritizing something else. They are breaking the data into shards. I mean, partitioning the data. The same data has been partitions distributed across the node. If you see the important thing in difference between both of them in their applications, and replication we discuss keeping copies of the same data. I mean the same data, I mean there is a whole data we have and we are putting the same data on multiple nodes. Benefits, they are reducing the latency, improve the reliability and availability, but increasing the scalability only in readers. But here the problem or the challenge is again the data changes. When the data is static, there is no problem. But when data is consistently upgrading, so there is a very heavy challenges. Like all copies must be updated on multiple nodes. But here the difference on the shard, if you see in the shard, we are discussing mainly breaking data into shards. Okay, we have a certain data, we are putting the same data into shards or partitions, and then the same shards or partitions are distributed across the nodes to improve the scalability. So here they are almost keeping all the features of the reliability and low latency, but here we are more focusing on the scalability. The goal is that the data access together should be in the same shard, minimize inter-node communications. So the main idea is one of them is that between the nodes or multiple computers, we have multiple geographic locations or data centers. So they are minimizing the inter-node communication. So a certain shard or partition can be put on a multiple nodes or distributed across the nodes. And the goal is to increase the scalability. Okay, improve, the main thing is here to improve the scalability and also to minimize the internode communication and maximize parallelism also here. So we are more focusing here. Parallelism means in terms of to access to data parallelly by multiple users. So typically combined with replication. Here we should not forget about it that this is also combined working by the replication, the sharding. Okay. Okay. So in practice, replications and shardings are often combined. Okay, as we said that they come typically combined with replication. Though each data belongs to a single shard, it may be replicated on the other nodes. Okay, as we said, here we're not putting the complete data copy on a single node or multiple node like in our application, but here a certain shards or partition of a data are kept on multiple nodes but or distributed node. But the point is here a single data can also be, or a shard or partition can be replicated on a multiple nodes. So that's why the replication is come into the picture again, and it is combined with the replica. Sorry, in the sharding is combined with the replication. So we have three main approaches for the sharding. The first one is horizontal. Each data unit tuple document stored in exactly one node. This is called the horizontally sharding. Okay, different units in different nodes. So if you see like a unit of a data could be the possible like a tuple from the MySQL or document from MongoDB, store exactly one node in different units in different nodes. I mean, if you are giving the different units, it should be goes to the different nodes definitely. But the nodes here is most common requires reconstructability. I mean, if we are doing the same way, but this is quite common, we need to reconstruct them, okay, if the whole data is required by the user. In vertical, the different attributes stores in different nodes. Now from the data, we are storing the different attributes, so but the attributes here are homogeneous, like in a single column we have. So subunits together, but note here is it's less common, and they are using a affinity matrix for clustering. We will discuss what is affinity matrix later. And there is a hybrid method also in a combination of the horizontal and vertical, but this is more flexible. Okay, it's in practice we require a property called reconstructability, as we discussed in the horizontal sharding. So we need to reconstruct them back the data, because the data it is a complete set of data and sharded or partitioned on a multiple nodes. So we need this property of reconstructability, that each unit of data should be univocally reconstructible by appropriate composing the data across all the shards. Okay, so uh, the general idea of the sharding is that the data is often accessed together, should be stored in the same shard. Okay, I mean the general idea is that the sharding data is often accessed together. As we say that single data is sharded, okay, partitioned on multiple nodes. So the idea is we need to access them back together from the same shard. So this limits internode communications. Okay, most of the data accessed by the query is on the same node, and enhance the parallelism. We discussed already these things in the previous slide. If you see on the previous nodes, that they are also communication and limitation the internode communication and maximize the parallelism. And furthermore, in practice, it is hard to find the optimal assignment of a data to nodes. I mean, this is one challenge associated to the uh, partitioning or sharding, that how much amount of data we need to assign a per node. So require knowing all possible queries that can be executed. In some cases it is reasonable, and even if you know all possible queries, the problem is general. I mean in p I mean natural problem, it's hard, okay, to detect amount of data. Okay, a general approach for the horizontal sharding. So we discussed two types of or three types of sharding in the previous notes: horizontal sharding, okay, vertical sharding, in the hybrid sharding. Okay, so a general approach for the horizontal sharding is divide data by an identifier. Okay, now here in the key based horizontal sharding, we are uh, sharding the data horizontally by a unique identifier. So in the unique identifier key range sharding, okay, each node assigning a range of IDs and they have some benefits. It's simple, efficient range queries, but the cons is that unbalanced shards possibility. In hash-based sharding is the keys are hashed, data assigned by hash range. In the above, we are assigning a range of IDs, but here we are hash assigning by hash range. Okay, so it is uniformly distributing, but better scalability. But the cause is that no efficient range queries must scatter or gather. So this is the key-based horizontal sharding by unique identifier, but we can also do it by secondary index of sharding, the same horizontal sharding. In the secondary sharding, if you see by the indexes sharding, the first one, if we are going by document, and the second one is by term. Okay, by document, it is fast update, only local shards indexes, and it reads, I mean, this strategy by documents, they are writing very fast, updates only local shards indexes, like each shards maintain its own secondary indexes here. In a shard, we keep the list of a unique identifiers corresponding to each value of a secondary index. So that's why it's fast. So in the reads, it is slow, scattered, gather across all the shards. So that's why they are going for the data to read from the multiple nodes, because the data, the same data is in the shards or in partitions in across multiple nodes. So read is slow, but write is fast. Okay. Note each shares has its own local second index. We discussed by term. If you see by term here, the writes then become a slow, update global index across shards, but reads here is fast, fast query only relevant shards, but many distributed transactions for updates. So again, here we are facing the consist problem. Okay, so the consist problem is coming from the leader selection. If you see in the single leader, in the multiple, not in a multiple leader, in between the multiple leader, we are having the problem of the conflict resolution. So here again, we faced that the secondary indexing sharding by term. So me need to distribute a transaction for updates. So here's the consist problems arising. So we have a consist algorithms. Later on, we will be discussing them. Okay. As we said that we will be discussing the affinity matrix, we have seen before this here. Like vertical shardings are less common, so they are using affinity matrix for clustering. So far we were discussing the horizontally matrices by partitioning of the partitioning by a unique identifier and second index sharding. In the unique identifier, we discuss key range sharding and hash-based sharding. In the index sharding, we discussed by documents and by term. But here, vertical sharding the affinity matrix, how this is working, we are computing affinity between the pairs, between pairs of attributes, how often access together. Then we are building an affinity matrix, matrix A, where A, I, J is equals to affinity of attributes of I and J. So cluster rows using spectral clustering and or any graph clustering algorithm. So attributes in the same cluster is same shard. As we discussed before that deciding the amount of the data, it is difficult. So optimal sharding, it is NP hard and natural prob hard in general. So this is how affinity matrix is working. Now important concepts we are going towards in the, it's called after the sharding, it is 4.4, and we discuss completely about the sharding applications. Now we are going to consensus, and it's really important because we have seen the consensus problem in different places. And this lecture will be finished by the 16th of pages. What is consensus basically? Here, if you see the consensus in the previous slides we have, or the notes we have seen many examples of the consensus problems like selecting a new leaders. It was in the single leader replica, and how we should decide the most up-to-date data in deciding whether an operation is successful. In the leaderless, we decide with the quorum, but there is a problem of consensus still arising. And as we have seen by the sharding index, second index sharding, we have seen by term in how we will be know that the distributed transactions for updates has been occurred. So we need to know that when the transaction has been succeed or fail, which is nothing but a consistency or atomicity, because atomicity we discussed that the transaction is either all or nothing, either it should be committed or it should be nothing. I mean, abort or rollback, in deciding whether the version of the data is correct in the version control. We have seen in the previous like how we were solving the conflict resolutions in the different replica methods like single, multiple, or leaders or leaderless in the version vectors. So I mean how the version vector is correct. So all these needs are consensus, okay? So in the consensus, if we see there is a in in all of these cases which we have discussed of the consensus, we need all node to agree on something, and especially in distributed data management. Typically, some of the data, this is one of the most important concepts in distributed data management system. Either all of them agree that this is, I mean, uh, the data which we are committing is either okay or it should be rolled back. It's really important in major. We will be discussing the Pax's algorithm also, which is a consensus algorithm. But let's discuss some of the concepts before further discussing the notions of consensus like Faxon or Lempo timestamp. So it is worthwhile that re-examines our notions of a consistency in the Cobb theorem. In the Cobb theorem, we discussed the um, availability and the consistency. So we actually saw two definitions, okay? One of them is linearizability, okay? Linearizability, it is a consistency in a Cobb theorem. So meaning data management system appears to have a single version of data equivalent to centralized system, like if it is a linearizability. But the COF applicability is subject to COF cannot guarantee all of them in together. If you remember that the COF theorem or Galbraith, if I'm not pronouncing incorrectly its name, so he discussed that this Brewer Galbraith, okay, Brewer Galbraith says that keeping all of these three at same time, that it should be the partitioning tolerant, it should be consistent or available. It's not possible. As we know, the partitioning is due to network, it's unavoidable. So we need to choose between the availability and consistency. So this is basically called linearizability, and it's mostly occurred in the centralized system. But if you see the convergence, in which is definitely eventually consistency, okay, in convergence operations preserve causal orders, okay. Here the operations are happening in the sequence like cannot see b before a if a cause b. So the COF capabilities is not subject to COF, can be I mean c a can be simultaneously, okay, consistency or also availability. So it could happen simultaneously in this case. Okay, the linearizability seems to be an appealing guarantee, as it would make our distributed data management system equivalent to centralized one. We already discussed these things that it really making like the traditional centralized system, so there is no risk conditions. Indeed, linearizability has several applications also that implemented distributed logs. Okay, one node can acquire a log. In all nodes agrees on who has the log. For example, leader election. This is one of the important aspect. We need to use the linearizability. to act like a centralized system and ensuring some piece of data is unique in avoiding risk conditions. Our process tries to always access some data before it is created or updated. Yeah, it helps also. At the same time, reliability may be too strong of a requirement, like in the Pascal theorem. If we say if there is no partitioning, then we are deciding between the latency and the available consistency. Okay, Carp theorem in both the Pascal theorem or Pascal, like you said, I'm pronouncing Pascal, but it is like Pascal. Okay, sorry for that. The facts is okay. Lampo start. Okay, Lampo timestamps. Lampo timestamps. Each node has a unique ID. Okay, this is now the consensus, one of the method through which we are implementing the algorithm. Okay, Lamport timestamps. So COP theorem and the theorem was Pasalek, okay, which was developed by Abadi. So let's start. What is Lamport timestamps? Each node has a unique ID in a counter of operations performed. But in the Lamport timestamps ID and a counter, they should be in the order sequence like ID 1 or counter 1, and they should be less than or equals to ID 2 or counter 2, and same it is for all of them. Each node tracks the maximum counter seen across all messages. So, I mean, maximum counter sees across all messages update its own counter to maximum seen local plus 1 and impose a total order consistency with the causality. So they need to be in the order. So they need to be causal also. But here limitations orders order known only for posterior, not sufficient for the real-time uniqueness guarantee. That is one of the limitations of the Lamport timestamps, but conceptually similar to version vector algorithm, but serve a different purposes here. It is used to impose an ordering on operation rather than discriminate causal relationship. So over there, I mean, here we are mainly implementing the causal relationship. They should not to be discriminated in the causal relationship, but over there we are imposing an ordering an operation here in the vector version. Okay. Another one is Pax's the consensus algorithm, which is basically working in 4 phases like prepare, promise, accept, and accepted. So if we see the first phase, prepare phase like proposer, like prepare also called proposers, guarantees a unique ID in which should be larger than any previously used, sends prepare into quorum of acceptors. Then in the promise acceptor, if n is greater than any previous ID seen, as you see, we discussed that the n should be larger than any previously used. Okay, if it is like that condition, so promise to ignore the proposal, they will accept this one. But if it is the ID less than the n, send back highest previously accepted value, if any. It could be dependent on the anyone, which is the last one, the previously used with the larger one. Accepts the proposers now. Okay, the first phase was prepare, now second promise, and the third is accept. So proposer having a quorum of promise now, the proposer also giving the quorum of promises. If any acceptor return a previous value, okay, let's suppose Z, so send accept in Z, else send an application, send an accept of in V. Okay, this is the else case. And if we see the accepted, like which is the phase 4, or we can call the phase 2, if we see these phases are divided differently, the first prepare and promises are phase 1 considered, and in the phase 2 we are accept and accepted. Okay, so initially both of them are considered like the preparation phase, and the last one is the exception phase in the consensus of algorithm. So acceptor accepts in X if it hasn't promised to ignore the proposal with the ID less than or equals to n. So sender accepts to proposal in learners. So this is the idea of the Faxes consensus algorithm. how it works. But here's the key idea that the fixes ensures the total order broadcast. Total order broadcast. If a message is delivered to one node, let's suppose it is delivered to all nodes in the same order. This enables serializable replications in serializable. And this is the main and key idea in the faxes algorithm. Okay, so we discussed the faxes algorithm of the consensus. We have now further the formal consensus requirement. So we call them preparation or properties. Okay, like how formal consensus, what are the formal requirements of the consensus? Okay, like how it should be made a decision on the formal consensus requirements, in what are the properties they need to be validate to say this is the consensus how we are making. Okay, the first one is uniform agreement. No two nodes decide differently. I mean, all of them should like, okay, uniform agreement. If they're deciding one leader, so the other should not consider themselves as a leader, like in the split brain. Integrity, no node decide twice. So only once they need to decide, like if they're deciding twice, so maybe they can change their leader. It is an example I'm saying, like in their application. So validity, any decided value was proposed by some nodes also, so it should be valid. In the same termination, so every non-crashing node eventually decides. I mean, let's suppose if there is anything happening in the failure of a leader, so they need to decide with the one who is with the most up-to-date data or recency. So this is the formal consensus requirement, some of the properties. We are almost at the last phase of this distributed data management system. So we are having also distributed transactions. So in the distributed transactions, this is one of the important concept. An ACID transaction across data stored on a multiple nodes. Okay, so far it was in the same. We discussed ACID transactions, but here the ACID transaction is now on multiple nodes. Okay, like it should be shared, replicated, or both. So, I mean, we discussed already application and shardings are working in combined typically. Okay, but here we have one problem, atomic commit problem. What is an atomic commit problem? Either all nodes commit or all abort, no middle ground. We know this from the ACID of the transactions in the atomicity. Atomicity, we discussed that either it should be commit or it should be rollback or aborted. So the same is happening here. It's called atomic commit problem. Why called atomic commit problem here? Because we are now on multiple nodes. So that's why all of them should agree on one thing, that either it should be committed or it should be a rollback or aborted. Okay, all or nothing rule. The same again we are applying here. So ACP, like we know, ACP availability, consistency, and parsing can be solved by using Pax's algorithm, but we have specialized approaches. Okay, so far we have seen that the such kind of problems when it arise in the consensus we try to solve with the Pax's algorithm, but we also have a specialized approaches like 2PC. 2PC is like the thing two phases committed. Okay, it is the same like we have seen in the faxes. The first two phases was for the preparation promises, and this last two was accept and accepted. Okay, but it's a little bit different from that. So phase one is prepare, and again prepare, and the last one is committing. So in the first phase of the prepare, we say there is a node, but it's specialized or coordinator. So one commit request, the coordinator sends prepares to all nodes. Okay, let's suppose if one is sending a commit request, in this case, all of the coordinators needs prepare to all nodes, and they letting they know they are now acting the coordinator as a coordinator to let all the nodes that they should have to prepare them. Okay, In the phase one of prepare, node promise. Now node is promising either it should be committed from all of them or they should have to respond of the rollback or the abortion. Node sends promises only if 100% certain it can commit in persist. Okay, I mean they should commit in persist even though even through false. If any node can promises transaction is aborted. Like we discussed, if anyone is says abortion, so all of them should say abort. It's all or nothing rule, okay? But in phase two commit pro in the commit stage, if we see the coordinator decision, if all node, let's suppose promised for the coordinate for to the coordinator for the committing, so point to list the transaction log. Now it's time to record the in the transaction log. But here two questions are arising. If node is not reachable, it will again and again ask until they should have to recover. And same question goes for if the coordinator fails, and the coordinator should have, and they are waiting for the coordinator until they are alive, or they recover back. And this question can also be addressed below here again. So commit in the last phase of the commit, phase two committing we are now. So commit or abort broadcasted like let all the nodes know that what happened. Okay. So the coordinator sends a decision to all nodes, keeping retrying until all acknowledges. So even they are receiving back, they all acknowledge from all of them that whatever decision has been made by all of them, either it's abortion or the committing, but they should have to even to receive the acknowledgement. But in the two-phase commit problem, we have a critical weakness. What is that? Once a node has promised, it is locked here in like a centralized system. Okay, it must wait for the coordinator's final decision. What the coordinator decides. If the coordinator fails after the commit point, let's suppose one coordinator fails in other nodes or the coordinator themselves decide the committing point. But before notifying nodes, all nodes are blocked in doubt until the coordinator recovers. So this is the weak and most critical weaknesses of the two phases committing. Last but not the least, we have a short note. In consensus, algorithms are very useful to ensure the consistency and reliability of a DMS or its subcomponents. We discussed that advanced DMS are a unified system, so they are working as an interoperate. So we are looking for the consistency of the and reliability of the whole components of the DMS. Also introduced costs at the same time, okay, which can impact the latency at the same time, and the response to the user will be slow. In practice, we need to consider trade-off. Yeah, it is a good dealing. We also discussed the same in the COP in the Pasalic theorems. So that will be really nice, by, which is developed by Abadin. Really sorry for the initial bad pronunciation of that one. I mean, I totally forget how to pronounce. Okay, indeed, we should have to uh, decide between as a trade-off, the usefulness of the consensus method depends on the application also. I mean, as they are really good for the consistency and reliability in its all components of DMS, but they have a cost also. So I mean, the cost is the latency, which is a bad user experience. So we need to decide the usefulness according to the application. And did NoSQL database do not provide support for distributed transaction? Yeah, that's for sure, like MongoDB. So more practically, if we decide the need of the consensus in our DBMS or DMS, uh, so the good practice is not to implement the algorithm from the scratch. So we all already have some certain types of solution like Apache, Zookeepers, or etcd, or the algorithms which so far we have seen, like in above. One of them was the Lamport time stream, but they were also having some limitations. Maybe it could not be reflected in the application which we are developing, like the limitation was order known only posterior, not sufficient for the real-time uniqueness guarantee. but we discussed that it's more working like this inversion vector. But the difference is here they are discriminating, they are rather than to discriminate the causal relationship, over there they are only imposing and ordering operations. So that was the main difference, and we discussed the Fax's consensus algorithm. Maybe we can use this one. And last, we also understood about what is the formal consensus requirements, and its properties, like it should be uniformly agreement, okay, and integrity, validity, and its termination. This should be predefined. Then we discussed the distributed transaction, which is quite common in two phases commit. What is that? We discussed these things, and in the critical weaknesses of the two phases committing, and at the last about the consensus decision and what are the existing solutions choosing the consensus algorithm. So that's all, and thank you. Last but not least, again, really sorry for that. The theorem name I have mentioned here again. So it was a Cobb theorem and Pascal-like theorem. Okay, so Cobb theorem is mainly developed by the brother Galbert Lang, and the other theory, the Pascal-like theorem, is developed by Happardi. Okay, here is the name. So sorry once again, and thank you so much. Bye.